students, welcome to Nuclear Physics 1 lecture number 11. I am Dr. Pervez Ahmed. In this lectures, we will have detailed discussions on the radioactive decay law. That is, we have to discuss about uh, n is equal to n naught exponential minus lambda t. So let's proceed towards today's lectures. The lecture topic just I mentioned is about radioactive decay law. So how we start? So you know that when a radioactive materials undergoes alpha, beta, or gamma decay, I mean this is a different type of radioactive decay, and we will have a detailed discussion about alpha, beta, or gamma decay later on in the course. So when we have such situations where a radioactive material undergoes alpha, beta, or gamma decay, the number of nuclei undergoing the decay per unit time is proportions to the total number of nuclei in the sample materials. Uh, that is, if we have n as total number of the nuclei in the sample, and delta n is the number of the nuclei that undergo decay and time delta t, then we have delta n over delta t is proportions to n. That is the relations. I mean that is the relation, that is delta n over delta t is proportions to n. Or we can say that delta n over delta t is equal to lambda n, where lambda is the proportionality constant, and we call that lambda as radioactive decay constants or disintegration constants. So later on we will derive the relation, the separate relations for lambda that we call the reactive decay constant or disintegration constant. Now the change in the number of nuclei and the sample is delta n, dn is equal to minus delta n and time delta t. Hence the ratio of change of n and the limit delta t tend to 0 is given by dn over dt is equal to minus lambda n. So this relations we get under the conditions. I mean we put the conditions just like we mentioned that the change in the number of nuclei in the sample is f. The change in the number of nuclei in the sample is dn is equal to minus delta n in the time delta t. So in this particular conditions, if we put the limit on the delta t, that is delta t tend to 0, then we have dn over dt is equal to minus lambda n. Or we can get dn over n is equal to minus lambda dt. That is, we have carried dt to the other side of the equation, that is on this side, that is from the denominators we have carried it to other side. Or we can say that we have multiplied both sides of these equations by dt. So dt cancel on this side and we got it on this side. So that's why. And on the other sides we divided both sides by n, that is divide this side by n and this side by n. So we get this final relation, that is dn over n is equal to minus lambda dt, and is a sample mathematics. Now when we have this relation, so now integrating both sides of this equation, this above equations, so we get, while integrating, so we have to integrate the relations on this side with respect to n by keeping the initials, by keeping the integrations between the initials and final value, that is n naught up to n, And similarly on this side, again we have to keep the initial value, that is from 0 to t, and lambda is constant, so we have to put it outside the integral. So that's why we have put it like this. So when you apply the integrations, so you get log n over n naught is equal to minus uh, lambda t. Now you know that here we have n naught and n. So what is n and n naught? So here n naught is the number of the radioactive nuclei and the sample and some arbitrary time t naught. I mean, it's arbitrary number. This and not indicate the any arbitrary number of the nuclei in the sample at some arbitrary moments of time that we denoted by uh, T naught. So what about N? So N is the number of the radioactive nuclei in any subsequent time. So you should remember about this N and N naught. So N is the arbitrary number of nuclei at any arbitrary moments of time that we denoted by T naught, and N is the number of radioactive nuclei at any subsequent time that we denoted by T. So what we will do next, we have to rearrange the above equations to get this particular relation. So what actually we have done is we have taken anti-log on both sides. So we take anti-log on both sides, so this will cancels, and here we will get uh, e, that is exponential, so anti-log, and then we have to carry a naught from this side to the other side of the equation. So we will get n as a function of the subsequent time t, that is equal to n naught, so exponential minus lambda t. So these equations, we call this equation as the law of radioactive decay. So whenever someone asks you about a radioactive decay law, so radioactive decay law is n is equal to n naught exponential minus lambda t. So let me explain it again. What is n naught here? N naught is the number of the radioactive nuclei in the sample at some arbitrary time interval t naught, and n is the number of the radioactive nuclei at any subsequent time interval t. Lambda is the decay constant, and t is that subsequent time interval. So this equation as a whole, this is known as the law of radioactive decay. So that's all we have for this lecture. Thanks for watching, but stay tuned for the next lectures. The next lecture will be the decay rate, that is r is equal to lambda n, and that will be lecture number 12. So stay tuned for the next lecture. Till then, bye bye.